Alright, so this is the video for Chapter 3, and for Chapter 3 we're going to be talking about linear inequalities. So we're just basically, right now we're just going to graph some lines and do some shading. So just like we did in Chapter 1, we just graph the line. We want to have it in slope-intercept form. Y equals mx plus b. So then if it is a strict inequality, meaning that it's just greater than or less than without the or equal to, in that case we're going to use a dashed line. Otherwise, if it's an inclusive inequality, like with the or equal to part, we're going to use the solid line. And if it's a greater than, we're going to shade above the line, and if it's a less than, we're going to shade below the line. Alright, so for number 1, we've got our inequality. It's in slope-intercept form. So we're just going to start by graphing it. So the y-intercept is at positive 1, and the slope is negative 3. So that means from there we're going to go down 3 over 1. Okay, and I could also go up 3 and to the left 1 to just get another point. And since it is or equal to, I'm going to use a solid line. And since it's greater than, I'm going to shade above the line. So if you look at the examples in the homework, they're going to tell you a more complicated way of figuring out where to shade it. Like picking a point and plugging it in and seeing if it's true and all that stuff. And that's fine if you want to do it that way, but to me this is a lot easier. I just know that it's greater than, so I shade above the line, like as if the line was a staircase. I'd be shading on top of the stairs. Alright, so the shaded area, it can be referred to as, that's the solution, or it can be referred to as the feasible set or the feasible region. And it can be bounded or unbounded. So pretty much if you only have one inequality that you're graphing, it's just going to be unbounded. Like number 1, it's unbounded because now that highlighted region really extends indefinitely, okay? So it's unbounded. Alright. So number 2, same thing. We have it in slope-intercept form, so the y-intercept is negative 3. So we plot that, and then the slope is 1/2, so we go up 1 over 2. And I'll just keep going up 1 over 2 a few more times, and maybe go down 1 and backwards 2. Now this one is strictly less than, so that means that I'm using a dashed line to graph it with. And it's less than, so I'm going to shade below the line, so underneath the stairs, or however you want to think about it. Alright, and again, of course, that's an unbounded solution area. Alright, now in number 3, the first thing we're going to have to do is put this into slope-intercept form. So I'm going to subtract 3x from both sides. So that would give me 2y is less than or equal to negative 3x minus 6. Okay, and then I will divide both sides by 2. So that's going to give me y is less than or equal to negative 3/2 x minus 3. So then I'm just going to go ahead and graph that. So the y-intercept is negative 3. And then the slope is negative 3/2. So from there I'm going to go down 3 and over 2. And then I can also go up 3 and to the left 2. And since it's less than or equal to, it's going to be a solid line. And since it's less than, I'm going to shade below the line. And again, that's an unbounded solution. Alright, and number 4, we're going to get it in slope-intercept form. So subtract 3x from both sides. And then we get negative y is greater than negative 3x plus 4. Then negative y is the same thing as negative 1y, so we would need to divide both sides by negative 1. Now, whenever you divide by a negative with an inequality, you have to flip the inequality. So this is going to change from greater than to less than. So it's going to be y is less than 3x minus 4. So when you divide by a negative number with an inequality, you have to switch the inequality symbol. Alright, and then we're just going to graph it. So we have the y-intercept at negative 4. Slope is positive 3, so from there I'm going to go up 3 over 1. I'll do up 3 over 1 again. And then I'll go down 3 and backwards 1. Okay, and it's strictly less than, so it's going to be a dashed line. And it's less than, so I'm going to shade below. Alright, still unbounded feasible region. Alright, number 5, x is greater than negative 3, so that's going to be a vertical line, and since it is strictly greater than, it's going to be a dashed line. And this is the only time when the above or below doesn't really apply, but since it's a vertical line, we know greater than, as far as x values, is going to be to the right. So we're going to shade to the right of this vertical line. Okay. Number 6, we have the y-intercept is at -3. The slope is -2, so from there I'm going to go down 2 over 1. Just do that a few more times. Go up 2 and to the left 1, and do that a few more times. Okay, and it is strictly less than, so it's dashed. And it's less than, so we're shading underneath. Okay. Alright, so now we're going to do some examples where we've got two inequalities that we've got to graph simultaneously. So, number 7, the first one is already in slope-intercept form, and the second one, all we have to do is just subtract x from both sides. So that would give me y is greater than or equal to -x plus 2. So for these where we have multiple inequalities, I would really recommend that when you're doing your homework and stuff, that you have some graph paper and like actually do the graph on the paper as opposed to just doing it on the computer, because I think that'll help you. So you can print out graph paper, you know, just Google it. You can print some out for free online if you want to do that. And you know, if you have a couple of different colors of like highlighters, that helps a lot. Okay, so alright, so the first line has a y-intercept at -3 with a slope of 1, so from there you're just going up 1 over 1. Alright, and that is less than or equal to, so that's going to be a solid line. Okay. Now, if you don't have, you know, different colored pens, and you know, hopefully you're doing this on a piece of paper, you might want to do something like label your lines as like A and B, so that will help you to not get them confused. Alright, now with this one it's greater than, so that means we would shade above the line. Okay, then the other one, we have the y-intercept at +2, and we have the slope is -1. And it's greater than or equal to, so it's a solid line. and it's greater than, so I'm going to shade above. Okay. So now this darker blue region is the solution, or the feasible region. Alright, and in this case it is still unbounded, okay, because it's going, forever, like in this directions here. So, okay, now when you're doing this on the computer, you're only, you can only shade the solution area. So that's why, if you shade all of this area, then they're going to count it wrong. You only shade the solution area. So that's why I think it really helps to actually do it on paper with like some highlighters. So that way you make sure you know what your solution region is. Alright, number 8. So on this first one, I'm going to need to subtract x from both sides, which would give me 2y is less than negative x minus 6. And then I would have to divide both sides by 2. So that would give me y is less than negative 1/2 x minus 3. Alright, and then the other one is good. It's just a horizontal line. Alright, so the first one has a y-intercept at negative 3 with a slope of negative 1/2. So from there, I'm going down 1 over 2, but I can also go up 1 and to the left 2. And it is strictly less than, so I'm going to be using a dashed line. And it's less than, so I'm going to shade below the line. Alright. Now the other one is a horizontal line at negative 3. So it's strictly greater than, so it's going to be dashed also. And it's greater than, so I'm going to shade above. Okay. And so this would be the solution. So when you're doing it on the computer, that would be the region that you would shade. Alright, number 9. In this case, I have 3 different inequalities. So on the first one, all I would have to do is just subtract x from both sides. That would be y is less than or equal to negative x plus 3. And on the other one, I also need to subtract x from both sides, and that would give me negative y is less than or equal to negative x plus 1. Oh, whoops. No, we keep going with that one. Okay, so we got negative y. That means we got to divide both sides by negative 1. So that would be y. And then remember, when we divide an inequality by a negative, we have to flip that inequality symbol. So instead of less than or equal to, now it's going to be greater than or equal to. So y is greater than or equal to x minus 1. And then we've got x is greater than or equal to 3. Okay. So first one has the y-intercept at positive 3 with a slope of negative 1. Okay. And it's or equal to, so we're using a solid line. And it's less than okay. Then the blue one has the y-intercept at negative 1 with a slope of 1. Alright, it is greater than or equal to, it's also a solid line. And it's greater than, so we shade above the line. Okay. Alright, and finally, x is greater than or equal to negative 3, so that's a vertical line at negative 3. It would be solid. And greater than, in this case, would be to the right. I love this problem because of all the pretty colors all together. I'm just weird like that. Alright. So, our solution is this black triangle in the middle. And in this case, the solution is bounded. Okay, so it's got boundaries on all sides. It's not extending indefinitely in any direction. Okay. So now we'll talk about linear programming. So basically, in linear programming, we have the inequalities, just like we did in these past several problems, and we're calling those the constraints. And then we have an objective function, okay, and we're trying to find the maximum and the minimum value of that objective function subject to the constraints. So the first thing we're going to do is just graph the constraints. Okay. So I have x is in between -6 and +6. So that's going to give me two vertical lines at -6 and +6. And so I know my feasible region is going to have to be in between these vertical lines. Alright, then I've got y is greater than or equal to -5. So that gives me a horizontal line at -5. Alright, and I don't want to shade us all in because there's too many different colors, and so I just know that my solution is going to be somewhere within this region, okay? But I don't really want to shade it, okay, because it'd be too much. Alright, now the other two, so the green one has a y-intercept at -3 with a slope of -1. Alright, so that's a solid line. Alright, and that's greater than. So I'll go ahead and shade above that, but I'll keep myself inside these other three constraining lines that I already know I'm supposed to be inside here, so I'll just stay in here. Alright, then the other one has a y-intercept at 4 with a slope of +1. And that is less than. So I would shade below this line. And staying inside these walls. Alright, so the red region is the feasible region, okay? So it is a quadrilateral, right? It's got 4 sides. So it's also got 4 corner points, okay? 1, 2, 3, 4 corners. Okay, so I'm going to list the x and y coordinates of the corner points. Alright, so up at the top is 6, 10, and then directly below that would be 6, -5, And then next to that would be 2, negative 5. And finally, this last one, that's a little bit harder to tell. So, to make sure of, I know that that point is at the intersection of the red line and the green line. So what I could do, if I set x plus 4 equal to negative x plus 3, and then I can solve for x to find out the x value at that point. So if I add x to both sides, it would give me 2x. So let's see, so I'm going to do plus x on both sides, and I'm going to do minus 4 on both sides. It's going to give me 2x equals negative 1. Divide both sides by 2, so that gives me x equals negative 1/2. And then to find out what y is, I would plug that in to either one of those. So let's see, I'll use the red one. Y equals negative 1/2 plus 4, so that's, we could just say 3.5. Or in other words, 3.5. Okay, so we have our corner points. We have 6, 10, 6, negative 5, 2, negative 5, and negative 1/2, and 3.5. So we're going to plug those into the objective function, which is z equals 3x minus 2y, to find out what z is. So 3 times 6 minus 2 times 10, so that's 18, minus 20 would be negative 2. And then 3 times 6 minus 2 times negative 5, that's 18 plus 10, which would be 28. And then 3 times 2 minus 2 times negative 5, that's 6 plus 10, which would be 16. And then 3 times 1/2, negative 1/2, minus 2, so it's going to be minus 2 times 3.5. So let's take out the calculator real quick for that one, I guess. So that's going to be, I'm just going to say negative 3 times, negative 3 times 0.5 minus 2 times 3.5. So that's negative 8.5. All right. So negative 8.5 is the minimum, which is located at the point of negative 1/2, comma 3.5, and the maximum is 28, which is located at the point of 6, comma negative 5. Okay. Number 11 is basically the same thing. We have the constraint that x and y are both greater than or equal to 0. So I went ahead and just used a graph that starts at 0, 0 and only shows the positive quadrant. And let's see, I'm going to have to do some work with my constraints to get y by itself. So the first one, if I subtract 2x from both sides, I'll get y is greater than or equal to negative 2x plus 28. And then on the blue one, I'm going to subtract x from both sides, which is going to give me 2y is greater than or equal to negative x plus 24. And then if I divide both sides by 2, I'm going to get y is greater than or equal to negative 1/2 x plus 12. And then on the green one, all I have to do is just subtract x from both sides, and that gives me y is greater than or equal to negative x plus y. Oh, and by the way, on our last problem, that solution set, of course, is bounded. Okay, so now let's draw our lines. So on the first one, I have the y-intercept is 28 and the slope is negative 2. So go down 2 over 1. And it's a solid line. And it's greater than, which means we're going to shade above the line. Okay, then the next one, we have the y-intercept is at 12. And the slope is negative 1/2, so from there I'm going to go down 1 and over 2. And it's a solid line. And we're going to shade above it. Alright, and the last one, whoops, I just thought I wrote that wrong. So this is a negative x plus 20. Okay, so the y-intercept is at 20, and the slope is negative 1, so just go down 1 and over 1. Okay, and we're shading above that one. Alright, so this whole big black region is the solution. So in this case, the solution is unbounded. Okay. It still has corner points though. 1, 2, 3, and 4. All right. Okay, so I think all these corner points are pretty easy to identify. We've got 0, 28. We've got 8, 12. We've got 16, 4. And we've got 24, 0. So I'll just fill these in on my table. Alright, then I'm going to plug those each into the objective function, which is 50x plus 10y. So 50 times 0 plus 10 times 28 is 280. And then 50 times 8 plus 10 times 12. Let's see, that would be 400 plus 120, so that'd be 520. And then 50 times 16 plus 10 times 4, so that would be 840. And then 50 times 24 plus 10 times 0. Okay, let me use my calculator for that one. That's 1200. So we have the minimum is 280. Now we cannot say that 1200 is the maximum because of the fact that the region is unbounded and the objective function has all positive coefficients. So, you know, all these points over here, all these points around here are all part of the feasible region, and they, you know, they're, so I mean 26, 0 would obviously have a larger value because you'd be doing 5 times 26, you know, and that'd give you an even bigger one. And you can just keep going, 28, 30, and you can just keep going forever. So you can just keep getting bigger and bigger values. So there's actually no max. Alright. Okay, so here is an application, it says a calculator company produces a scientific calculator and a graphing calculator. Long-term projections indicate an expected demand of at least 100 scientific and 80 graphing calculators each day. Because of limitations on production capacity, no more than 200 scientific and 170 graphing calculators can be made daily. To satisfy a shipping contract, a total of at least 200 calculators must be shipped each day. If each scientific calculator sold results in a $2 loss, but each graphing calculator produces a $5 profit, how many of each type of should be made daily to maximize net profits? Okay, so first thing that I think of is why are they even doing the scientific calculator if it, results in a loss? Well, I mean, I guess there could be a number of reasons. They may have a contract with Walmart where they have to, make the scientific calculators for a certain price, and, but maybe by doing that, then Walmart agrees to also buy their graphing calculators and sell them for profit, so who knows. Anyway, we're trying to figure out the number of each calculator. So let's define our variables and say that x equals the number of scientific calculators and y equals the number of graphing calculators. Okay. So they need to make at least 100 scientific and at least 80 graphing, but no more than 200 scientific and no more than 170 graphing. So, okay, scientific, 100 scientific, so x has to be between 100 and 200. And then y has to be between 80 and 170. And then a total of at least 200. So x plus y must be greater than or equal to 200. Alright, and then we have the objective function, which is the profit. P equals negative 2x plus 5y. Alright, so let's see here. I think if we count by tens, we should be good on the scale of the graph. Let's see. 10, 20, 30, 40. It's always best to scale your x and y axis with the same scale if at all possible. So that'll reduce confusion on your slopes and whatnot. Alright, so x has to be between 100 and 200. So that's going to be a vertical line at 100 and a vertical line at 200. Alright, so I know my feasible region has to be between those two vertical lines. And then similarly, y has to be between 80 and 170. So I got a horizontal line at 80 and a horizontal line at 170. Okay, so I got that box there, and my feasible set has to be inside that box. And then the last one, just subtract x from both sides, so y is greater than or equal to negative x plus 200. So y-intercept is at 200. Oops. Okay. 200 and 220. Okay. Alright, and negative x alright. Solid line. Alright, so it's got to be greater than that, but it's got to be inside the box. So here's my feasible region. And this feasible region has 5 corner points. 1, 2, 3, 4, 5. Alright, all very easily identifiable. Okay, so we've got 100, 170. And we've got 200, 170. And we've got 200, 80. And we have 120, 80. And 100, 100. Alright, so let's make a table. X, Y, and Z. Okay, so we have 200, 170, 200, 80, 120, 80, 100, 100, and 100, 170. So z equals negative 2x plus 5y. So negative 2 times 200 plus 5 times 170. Okay. So that's negative 400, whoops, plus 5 times 170 equals 450. Then negative 2 times 200 plus 5 times 80, that's going to be 0. And then negative 2 times 120 plus 5 times 80. So that would be negative 240. So basically 400 minus 240 would be 160. And then negative 2 times 100 plus 5 times 100, that's just 500 minus 200, which is 300. Negative 2 times 100 plus 5 times 170. So 5 times 170 is 850, minus 200 is going to be 650. Alright, so we wanted to find the maximum, maximize the profit. So we found that the max profit is 650. And they achieve that by producing (100) scientific calculators and 170 graphing calculators. Alright, so that concludes Chapter 3 video lesson, and I hope you found it helpful, and let me know if you have any questions. Thanks.